General relativity, step by step. I've got this rather nice line element here that behaves itself for the whole of R, whole of positive R at least. Of course, when R equals 0, something rather peculiar happens. We'll come back to that later. But we've still got the rather peculiar problem that P twiddles and Q twiddles, P twiddles and Q twiddles, are both null coordinates because the metric tensor is just a product of these two guys here. So we need to sort that out. And what we're going to do is to define a coordinate t and a coordinate x, and t is going to be a half of P twiddles plus Q twiddles, and x is going to be a half P twiddles minus Q twiddles. The reason we do this is that it will turn out that this is going to be a time-like coordinate and this one's going to be a space-like. But we don't know that yet. These are just suggestive names. So let's work out what t is. T equals a half, and then P twiddles was e to the p over 2, and Q was minus e to the minus q over 2. That's right. What was P equal? P was equal to, just looking through my notes here, T plus R plus log mod R minus 1. There are subtleties in this, and Q was equal to T minus R plus log mod R minus 1. So what does that leave T? T is a half of e to the 1/2 P T plus R plus log mod R minus 1 minus, it's an absolute inspired, the relationship between P twiddles and Q twiddles is a piece of absolute magic to me. There's no, I can't put it into a more sort of general context. It doesn't seem to be one of a number of transformations that you might use. It just seems to have been plucked out of thin air. I guess, yes, I guess these guys were quite clever. Anyway, it's minus e to the minus a half of Q over 2. Oh yes, we've got the minus there. And that's going to be T minus R minus log mod R minus 1. Close that bracket and close that bracket. So we've got loads of stuff to play with here. Equals a half x of, I'm going to factorize by R plus log mod R minus 1. And what have I got left? I've got, actually I'm going to put the half there. You'll see why in a minute. A half. And then we've got e to the 1/2 of t minus a half t from there. Have I got everything? The r plus log R minus 1 I've factorized out. Here a minus times a minus is a plus, which is this one here. And we've got a half of that. So that's equal to x of r. Oh no, there's a half missing. Half, and I'll put over 2 there as well. 1/2 r plus log mod R minus 1 times, this thing here is hyperbolic sine of t over 2. You'll recall that sine x, shine x at least, equals a half e to the x minus e to the minus x, and there's another one called cosh of x equals a half of e to the x plus e to the minus x. And these are called hyperbolic sine and hyperbolic cosine because they bear the same relationship to a hyperbola as the regular trig identities, regular trig ratios do to a circle. So you use a hyperbola instead of a circle, and it turns out that these formulas are quite useful. So what have I got here? Well, I can just rephrase it slightly differently. I can say it's e to the r over 2 times the square root of r minus 1. I'll just neaten that up a little bit. The square root of r minus 1 times sine h of t over 2. Actually, it's not. It's the square root of the modulus. I'll write it in as a square root. And so this is a perfectly sensible thing. However, it's got the defect. It's got the defect that r being greater than 1 and r being less than 1 don't really behave themselves. In the sense that different positions in space-time will correspond to the same value of t, which is not really what we want. We need to be a little bit more careful about how we present this analysis here. And I've just casually chosen the principal branch for the log function here, but of course you'll be aware that log x, you can write 2 pi I plus log of x, and that's a generalized logarithm. You normally write it with a capital L, log, like that. Now if that's the case, then what happens is if we choose the other branch, then we add 2 pi I here, and dividing by 2 we get a pi I, which multiplies everything by -1. And so what that tells us is that if r is greater than 1, we have t equals this, but if r is less than 1, we can choose the other branch, and that will make our lives a lot easier. r over 2 root 1 minus r, and of course this will turn into a cosh t over 2. Why does it turn into a cosh? It turns into a cosh because if I introduce a factor of 2 pi I here, when I divide by 2, we're effectively multiplying by -1 here, so we get a plus term in the middle. Okay, well that's quite nice, isn't it? So we have that t equals, and we choose one or other transformation depending upon which value r has got, e to the r over 2 root r minus 1 sine t over 2 for r is greater than 1, and e to the r over 2 root 1 minus r times cosh of t over 2 if r is less than 1. And of course if r equals 1 it's just 0. And similarly one can define x, which has got the same properties here. Not the same properties, but it's almost the same. That's going to be e to the r over 2 root r minus 1, and that's the other one. That's going to be the cosh t over 2. Why is it going to be the other one? It's the other one because I will be using the other definition for x where there's a plus instead of a minus. So the only difference between the t and the x is the sine goes to a cosh and the cosh goes to a sine. E to the r over 2 root, got it wrong way round. No, I haven't, that's right. And 1 minus r sine t over 2, and which way around is it? That's for r is greater than 1, that's for r is less than 1. And t and x are called the Kruskal Szekeres. I'm not sure exactly how to say it even now. Szekeres coords. Okay, stop there. T, x are these two coordinates here. Stop.